It's always a pleasure to come and talk about one's own science, and that when it is connected with a dear friend, it is even more exciting. I chose to talk about this, a tiny piece of work, because the time allotted is so short. Although I have given this talk to different audiences, this format is new, and therefore I hope this will be appreciated. Topic is, can droplets make soil? And that we all have been working on confinement, electronic confinement largely, but there can also be spatial confinement that gives a lot of surprises. And I came here because of Ashutosh. This person has been working on surprises. So I remember his Tibetan stories. I remember his gecko stories. I remember all those excitements which are all unexpected. Right? And this person, if you look very closely to his face, he is actually practicing attached detachment. And always attached, but you see detached. And right now I'm seeing detachment on his face. And I would like you to look at him closely to see different facets of detachment. Having said that, the topic that I wanted to talk about is this. Last year, for about 5 years, we've been asking this question: can droplets do something profound? And that took us to this. And so what is that story I'm going to illustrate to you in the next 12 minutes. We all know that big rocks make soil. A rock such as this is called a giant rock in America. It's about 22 meters tall. Meter scale rocks make millimeter scale sand particles over millions of years. And this happens, this is a meter to millimeter, is a scale of 1,000. So I asked this question: can droplets do this? Meaning, can droplets make micron scale sand to nanoscale sand, a scale of 1,000 in reduction? So before I tell you that story, I should tell you that I have been working on functional nanomaterials and droplets. So if you take a droplet and you put the right kind of ingredients, you can make nanoparticles. You can use these nanoparticles through spectroscopy, like surface enhanced Raman spectroscopy. My dear friend Kulkarni does it very well. You can arrange nanoparticles and create nanowires. And you can use these nanowire structures to capture humidity. We have a company on this. You can create two-dimensional structures. You can create three-dimensional structures. You can put different types of particles and rods, and phase separate them in a droplet. You can do spectroscopy to characterize this phase separation. So all these have been going on in the group. So one day I asked this question: can I convert one particle to another particle? And a student did this experiment. You can take a number of a collection of particles such as these, which you typically make in a synthesis, and through droplets, when I say droplets, I'm creating charged droplets through electrospray, an apparatus such as this. And I found that you can convert these polydispersed particles to highly monodispersed particles as you are seeing here. And you can arrange them. So, when you say large particles are broken to smaller particles, essentially you're saying that chemical bonds can be broken. So I asked this question, if hundreds of chemical bonds can be broken, how about a million chemical bonds? So that took me to this question, can I, in droplets, can I break a rock? And so when I asked this question, of course, to a student, if you have to tell, you cannot tell a student that go and break a rock. You should tell the student what rock to break, because rocks are plenty. Minerals are plenty. I work in the area of arsenic. So arsenic minerals alone, there are 10,000 of them. So what mineral or rock to break? So I looked at the mother of all rocks. So that is sand. Sand is quartz. So having realized that quartz is what you can probably think of or tell a student to break, and I asked, of course, the student to go and get the right sand from my friend, who's a Muslim Tani, is dean of our sponsored research at IIT Madras, a civil engineer. So he gave the sand. So this is called Endo River sand. You break it, you grind it, and they micron scale particles. They look like this, tens of microns. And you put it in water, suspend it, and apply a potential. And the needle that you're seeing is 50 micrometer in diameter. So droplets are formed and they are charged. And you are surprised that at the end of these process, you collect these droplets on a TEM grid, transmission electron microscopic grid, and you apply a potential of 4 kV. And D image is the sand that you start with. C image is the broken sand that you begin with the experiment. D is the nanoparticles you get. See rocks of quartz break down in water droplets. Oh, is it so surprising then? Can I break all rocks? Then I go to a friend of mine who is a minerals expert, and he keeps a gemology institute in Chennai called Chennai Gemology Institute. He gave me 140 gemstones, different types of gemstones. One gemstone is ruby. Grind it again, make micron scale particles, put it in these droplets. Yeah, it also breaks and forms nanoparticles. How about corundum? How about synthetic aluminum? How about a whole host of such materials? They all break. So today, the story is that anything can break, including diamond. Okay. So also it's possible that these broken pieces, your surfaces can be controlled. You can create anisotropic particles. You can increase the surface area. Oh, this paper was fascinating, but then how can I sell this paper? Nobody will take this kind of a crazy idea. So I asked my friend Himesh Wagmare, ANCASR, asked him, can you try to understand this? So he calculated how it breaks. So we calculated the energy, and this the energy that you see there is the energy of cleavage. But it is also possible that the surface or materials such as this can cleave by slip, not really break, but slip, a series of successive stacking faults. So we calculated energy needed for such stacking faults, such as a crystal undergoing stacking fault. And this apparently turned out to be much, much lesser than the cleavage energy. And we calculated how this cleavage can be enhanced by protons, because water droplets contain protons. And if you increase the protons in the droplet, the cleavage becomes facile. And in a droplet, if you apply protons or electrons, you create electric fields. This increased electric field can also enhance this feasibility of cleavage. So we studied all that. So I'm going to cut out this long story just to tell you that when it breaks, it also releases pieces of silicate. You can detect these pieces of silicate by mass spectrometry, and you compare these features with standard mass spectrometry. So it is indeed possible that in a droplet you can break minerals. Now, what else you can do? Droplets, of course, are acidic. You're standing in the rain, you're actually getting slightly acidic ones. When the droplets are very tiny, it is even more acidic. And can acidic, water droplets can do something to these rock particles? Of course, there is some corrosion that is happening, that is what is seen there, but no nanoparticles are formed. So what we said was that the droplets with minerals, in the course of their trajectory or flight, when the droplets become what are called daughter droplets by Coulomb fission, when the surface energy cannot hold the charges, or repulsion between the charges, they break down. Along with that, you get nanoparticles. But there are many interesting things that are happening, as one point in time Raleigh talked about. So when droplets break, there can also be big pressure fluctuations. These pressure fluctuations can be of the order of 200 to 300 megapascals. And these pressure fluctuations are indeed the reason for triggering these breakage, but it is also possible that protons can enhance it. And someone wrote a perspective on this. Today, a few months ago, there's a paper in Nature which talked about what happens on the surface of droplets. What kind of electric fields are present? Somebody measured it with Raman spectroscopy. So there are interesting science, aspects of science that is evolving. Today, we ask this question, as droplets are breaking, can I capture, during the process of this particle fission, an in-between state when particles are separated? We can capture it. It's also possible that many other minerals can be broken, synthetic materials can be broken, graphene can be broken, WS2 can be broken, MOS2 can be broken. In the course of breakage of these particles, you can see the course of this change. Every bit of it can be captured. So why is that we are interested in this? I want to tell you that if we are in a position to break droplets, break particles to create nanoparticles, nanoparticles are the active ingredients of soil which transport silica. And silica are essential ingredients of rice or wheat, because 15% of silica is what makes rice stand up. Is it possible, by using wastewater, can you convert sand to active silica and convert deserts to, fertile fields? So we are working on this large vision today, with building science, to technology, to societal applications. This is where I resonate with Kulkarni, Ashutosh, and company, that what is born in the laboratory should be taken to masses in a very big way, for which India may not be mature right now, but we are the ambassadors to make the country move forward. I said that natural minerals break spontaneously charged water, microdroplets. It occurs only in water and not in any other solvent. A variety of studies, variety of materials show that this actually happens across facile due to proton-induced slip. Detailed investigations are essential to understand this process in detail. Specific nanomaterials in soil can change probably agriculture. And I must tell you that science that is done in the laboratory with milligram quantities of materials can of course be translated, as we have shown that we are today making 100 tons of nanomaterials per month. Using this, and we are taking nanomaterials to feed, to remove contaminants from water and supplying clean water to people. This is a village shop in Punjab. There are 17,100 of these installations, across the country. So to do this, it is important to have data on water. So we are today building, by using students and their enthusiasm, build a water atlas of the planet. And if we know how water is contaminated, we do have technologies to solve this. And we are on that mission. I have a video, but unfortunately, I don't have time to show you, and connection is not working. Let me tell you that this entire science was supported by Department of Science and Technology. Therefore, I have another reason to thank Ashutosh, by a great team of students and fantastic students, great institution, great collaborators. Thank you very much.